Hello, I'm Hakim, representing a team of 3 from University Putra, Malaysia, with Ms. Nur Fazlinda Othman, as well as the team lead, Dr. Muhammad Effendi Yaakob. This presentation is about statistical model on heat stress under agrivoltaic condition in Malaysia, a tropical field assessment. Basically, we analyzed some heat stress data under agrivoltaic condition utilizing the statistical models as well as the machine learning algorithms to share with you guys some insights from Malaysia. So, a bit about the introduction. Photovoltaic or PV technology as an alternative energy mix with agri-based activities is so new in Malaysia that the Malaysian government has been actively promoting the adaptation of such technology. So we at the University Putra Malaysia utilize this technology adaptation with crop plantations. And one thing to consider, an event which is so significant in crop plantation is called heat shock or heat stress, which occurs normally at a temperature 10 to 15 degrees above ambient. So to understand more about heat stress in Malaysia under agrivoltaic condition, we collected some data throughout 5 continuous days with 18 hours each day with 1 minute intervals. So then we analyzed the data using some statistical analysis and machine learning algorithms to estimate the distribution parameters and also to develop some predictive models of heat stress. Alright, so this is the site setup at the University Putra Malaysia. It's called Hybrid Agrivoltaic System Showcase, HAVs, at the Faculty of Engineering, where we have PV panels. Here we have the crops underneath. This crop is called Orthocephens terminus, and we have sensors at different heights from the ground. We have sensors to measure the temperature on the ground, 1 feet from the ground, 2 feet from the ground, 3 feet from the ground, 4 feet from the ground, as well as below PV panel. Not to forget, we measure as well the ambient temperature. So, what are the insights? So some of the insights here we can portray using this figure, where we have different lines across time in minutes representing different temperatures at different heights. Alright, so we have here temperature on the ground, temperature 1 feet from the ground, 2 feet from the ground, 3 feet from the ground, 4 feet from the ground, temperature below PV panel. We have also temperature at ambient. And this is the most important. We have here heat stress occurrence, which is 10 to 15 degrees Celsius above ambient. Alright, so intersection happens between lines with the heat stress region, meaning that at that particular temperature heat stress occurs. So we have here intersections of this red shade between with the blue lines as well as the brown lines, representing temperature below PV panel as well as temperature 4 feet from the ground. To understand it more, or to simplify the diagram, we used heat map. Alright, heat map with temperature at different heights again. Temperature on the ground, 1 feet, 2 feet, 4 feet, 3 feet, 4 feet below PV panel. And we have different levels of sun. Early sun, moderate sun in the morning, peak sun, moderate sun afternoon, and we have mild sun in the evening. So basically, different colors representing the different density or different level of heat stress occurrence. So the brighter the color, it means the more heat stress is happening. So here we have the brightest color here. It means that the most heat stress occurs at temperature 4 feet from the ground during peak sun. All right. Looking at this diagram, we know that only at two different temperatures heat stress occurs. One, temperature at 4 feet. Two, temperature below PV panel. Because here we don't have any intersection at all. I mean, we have zero heat stress occurs in the dark region. So we simplify this significant heat stress occurrence into this diagram, and then we can see that, just to see whether there is some coincidence of insightful trends, but there is no redundancy in both of the lines, but we can see that there is some kind of pattern still, and this is time by hours. So to understand more about heat stress of these two temperatures at 4 feet and below PV panel, we assessed the normality of both temperatures. Firstly, using histogram. This is the most traditional one, right? So we can see here that it is extremely skewed, super skewed, the heat stress occurrence below PV panel. And also, heat stress occurrence at 4 feet height from the ground also extremely skewed, which means they are not normal. So then we analyzed the data using QQ plot for normality assessment. And we can see again that the points are not at all lying along the straight line, right, for both temperatures. And then we just want to confirm that using some multivariate and univariate normality tests. We can confirm them based on this p-value of different tests that we conducted: generalized Shapiro-Wilk, correlation with Levi, Kolmogorov's-Smirnov. So basically they are not at all normal. Based on this diagram, you can see that they are extremely skewed, so we used some skewed distributions. We assessed the fitness of heat stress occurrence in different distributions, and you can see that the p-value here means that generalized Pareto is the most suitable, because the p-value for below PV panel is the highest for generalized Pareto. You can see here, right? Highest, and 4 feet also highest here. Then we simply visualize them to compare the empirical, the blue bars, with the true generalized Pareto density of distribution, the orange line. So we can see that there is some kind of fitness here for both temperatures at different heights. Then we estimate the parameters of generalized Pareto using heat stress occurrence data, and for both parameters we have here the estimates, and then we simply substitute the value into the cumulative density function of the generalized Pareto distribution. So we have two different CDF here, which represents CDF below PV panel and 4 feet height from the ground. Next, we model the data to predict heat stress occurrence at both temperatures using some machine learning algorithm. So this is below PV panel, this is at 4 feet height. So we utilized 22 different machine learning algorithms, which are basically random forest, regression, we have support vector machine, we have kernel methods, we have neural network, NN. Alright, so we utilized the main performance metric of root mean square error, RMSE, to determine the best model. Aside from that, we also utilized R squared as well as mean absolute error. And we found out that model average neural network is the best, with the lowest RSME, with the lowest MAE, and with the highest R squared. And the predictors we utilized are temperature on the ground, temperature 1 feet, 2 feet, 3 feet, 4 feet from the ground, which means we don't utilize the temperature below PV panel. Next, to develop a heat stress occurrence model at 4 feet height, we exclude the temperature at 4 feet. So we include only T on the ground, T 1 feet, T 2 feet, 3 feet, and below PV panel. So using the same algorithms, we can conclude that radial persist function kernel regularized least squares is the best with the lowest RSME. It has the second highest R squared and the sixth lowest MAE. So that's all from me. Thank you.